Okay. Hello everyone. I am Li Tao Zhou from the University of Hong Kong. I am here on behalf of the author Yao Da Zhou, who is currently having a sore throat, to present his work revisiting iso-recursive subtyping. So this work is done by Yao Da Zhou, Jingxu Zhao, and Bruno Oliveira, originally published in Uppsala 2020, and we also have a journal version that is published on Toplas this year. The focus of this paper is recursive types. So recursive types we denote as mu alpha tau are used to represent recursive data structures like sequences or trees. So for example, the binary tree with integer leaves is encoded as the sum of int and the product of tree and tree. The list of integers is encoded as the sum of unit and the product of int and list. And these types are recursive in the sense that the type itself appears in the type definition. So a key question is, what is the relation between the type and its one-step unfolding, where we replace the recursive type variable in the type body with the recursive type itself? So there have been two interpretations of recursive types. The Eki-recursive types consider a recursive type and its one-step unfolding are equal, while the iso-recursive types consider a recursive type and its one-step unfolding are not equal but isomorphic. So in the iso-recursive setting, a recursive type and its one-step unfolding are converted by a term-level fold and unfold operation. So the fold operation will construct a recursive type from its one-step unfolding, while the unfold operation will open a recursive type to its one-step unfolding. And most mainstream languages employ an iso-recursive setting, which is also the main focus of our paper, the iso-recursive types. And for example, the code on the left-hand side is a piece of Haskell code. So here the data type list can be regarded as a recursive type, and the use of the constructor nil or cons can be regarded as a fold operation that creates this list data type. And what happens when we implement this map function, we do the pattern matching, and it can be regarded as an unfold operation. Another example is a piece of Java code on the right-hand side. So the class shape can be modeled by a recursive type. And because the class definition, so in the class definition, we also have the class name shape in the class definition. Yeah. And the class, here this class definition itself can be regarded as obtained by a fold operation. And when we invoke a method of this class, it will require an unfold operation. Now, since we have recursive types, it is desirable to have recursive subtyping. And a natural question is, can we define subtyping relations between recursive types? So let's have a bit of history here. The first subtyping for recursive types are the Amber rules by Luca Cardelli in 1985. And the most famous comprehensive study of recursive subtyping is from the paper Subtyping Recursive Types by Amadio and Cardelli, published in 1993. In their work, they study how to compare two Eki recursive types in the lambda calculus. And if we choose a tree view of Amadio and Cardelli's algorithm, it says that we compare two Eki recursive types by unrolling the recursive variable with unlimited times, and then checking the subtyping between all components in the wholly unfolded tree. So for example, the tree on the left-hand side is an unfolded tree for the recursive type mu alpha top to alpha. And the tree on the right-hand side is the unfolded tree for type mu alpha net to alpha, and it can also be the unfolded tree for its one-time unfolding, which is essentially mu alpha net to a recursive type, which is mu alpha net to alpha. And both subtyping relation will hold in the sense of Eki-recursive subtyping. And if we write down the subtyping rules for Eki-recursive subtyping, there are four key subtyping rules we choose to present here. And the most important rule is the recursive rule. It says that if we check whether two recursive types are subtypes, then we just need to check if their recursive bodies are subtypes by assuming that the subtyping relation holds between the recursive variable. And we also have the assumption rule, which says that two recursive variables are subtyped when their subtyping relation is stored in the context. And note that the transitivity rule is also required to be built in. And the recursive Amber rules also have a special reflexivity rule in which another set of rules are defined to check if two types are equal. So in the notion of this special equality relation, mu alpha net to alpha, for example, mu alpha net to alpha, and is equal to its one-step unfolding. And there are also some other equality relations that will hold in the sense that they are equal when unrolling to the limit. So here, for example, mu alpha net to alpha is equal to mu alpha net to alpha. So we skip the detail about this equality relation here and move on to the iso-recursive subtyping in our paper. Okay, so the most widely used subtyping rule for iso-recursive types are the Amber rules by just changing the reflexivity rule from that special equality relation to a syntactic equality relation. And the only difference for the iso-recursive Amber rules is in this reflexivity rule. So two iso-recursive types are subtypes if they are syntactically equal. This helpful trick on the reflexivity rule makes the iso-recursive Amber rule simple, fast, and easy to implement. But there are also some drawbacks. So first, reflexivity cannot be eliminated. Assume if we want to check two identical recursive types are subtypes, where the recursive variable are appearing on the contravariant position. So without reflexivity rule built in, we cannot get a successful derivation, because here for this example, we can only apply the recursive rule. And by having alpha less than beta in the premise, in the context, we cannot derive the contravariant subtyping for the recursive body. And secondly, the transitivity elimination is non-trivial, which means that we cannot simply drop the transitivity rule. And even the proof of transitivity and other lemmas are also difficult. And there are no mechanized proof for Amber rules before. And the only proof for transitivity that we are aware of is very complicated. And finally, since we have a special form of in the context, this subtyping relation assumption in the context, the proof for Amber rules is not modular, which means that the proof cannot be easily extended to other systems with those standard subtyping relations, and we cannot just reuse the existing proofs when doing this extension. So before continuing to introduce our approach to solve these issues in iso-recursive Amber rules, let us first have some intuitions about what kinds of recursive types are subtypes. So there are some facts we should know. First of all, any type should be a subtype of itself, whatever the positions of the recursive variables are. And secondly, the positive subtyping should be accepted. By positive, we mean that the recursive variable always appear on the positive relation. So for example, this subtyping relation about mu alpha top to alpha and mu alpha net to alpha should hold, because net is the subtype of top and the same recursive variable alpha appears on the positive position. And thirdly, many forms of negative subtyping should be rejected. So for example, this mu alpha to net is not a subtype of mu alpha to top, although net is a subtype of top, because it violates an important property which will break the soundness of a type system with iso-recursive subtyping. So this important property is what we call the unfolding lemma, and it says that if two iso-recursive types are subtypes, then their one-step unfolding will retain the subtyping relation. There actually is a single specification that we propose in our work that combines the intuitions above together. So in our work, we propose this new formal specification for iso-recursive subtyping, which is called the finite unfolding rule. So what we mean by finite unfolding is that we substitute the recursive variable in the bodies by their recursive body n times, where this n range from 1 to infinite. And more intuitively, our finite unfolding rule says that two recursive types are subtype if and only if all their n-time finite unfoldings are subtypes for any positive integer n. So let's illustrate this idea with a tree view we have used before. So instead of checking that the any pairs of subtrees in the fully unfolded type, as the Iso-Recursive Subtyping does, in the Iso-Recursive Subtyping, this checking only happens when we unfold the two recursive types at exactly the same n times. So for example, here is the tree view for one-time finite unfolding, and we can check that all the subtyping relation holds for the subcomponents. And here is the tree view for the two-time finite unfolding, and this check also passes. And then goes the three-time finite unfolding, and until the infinite time finite unfolding. So in the tree view, if we say that the Iso-Recursive typing is to unroll the recursive type to the limit, and then subtyping for the whole tree, then Iso-Recursive subtyping is to unroll the recursive types to the limit, and then checking the subtyping relation for all rank n subtrees. And here we show the difference between Iso-Recursive subtyping and Iso-Recursive subtyping with the concrete example. So we have seen that if we compare mu alpha top to alpha with both of these two types, the second type is the one-time unfolding of the first type, then both subtyping relations should hold in the Iso-Recursive subtyping setting, as reflected by the infinite tree model. However, under the Iso-Recursive setting, the type on the left-hand side is not the subtype of the second one, which is the one-time unfolding on the right-hand side, because this one-time finite unfolding does not follow the same structure of this type. So we can say that the Iso-Recursive setting accepts more subtyping relations than the Iso-Recursive setting does. So compared with Iso-Recursive AMBER rules, our new specification has many advantages, including, firstly, reflexivity is derivable from the rules, and transitivity and other lemmas is easy to prove. And we also enable modular proofs in our specification, and it can be applied to other non-antisymmetric subtyping relations. So our new specification is not algorithmic because it needs to test the infinite subtyping as we have seen. And therefore, we also propose a new algorithmic Iso-Recursive subtyping rule called the double unfolding rule. So actually, we have observed that the checking of all rank n subtrees in the finite unfolding rule actually repeats the process of checking the rank 1 and rank 2 subtrees. Therefore, we only need to check the one-time unfolding and the two-time unfolding, and then we end up with this algorithmic subtyping rule called the double unfolding rule. And the double unfolding rule is still not so satisfactory because we need to have two premises to check. And thus we propose another Iso-Recursive subtyping rule, which is called the nominal unfolding rule, that achieves the effect of doing one-time finite unfolding by adding this extra label. Here we use the red alpha to denote here. So when the two-time unfolding substitution takes place, this one-time unfolding check will also take place. So we have proved that the nominal unfolding is to have has the same expressiveness as the double unfolding in a simple setting like the simply typed lambda calculus, and can also lead to a simpler proof. We also prove that our new specification has the same expressiveness as Iso-Recursive AMBER rules. A direct equivalence proof is difficult, so we propose an auxiliary set of subtyping rules which we called weakly positive subtyping. And the key idea in this rule is to have a special rule for recursive types that checks if this recursive variable alpha appears weakly positively in the two type bodies being compared. What we mean by saying a variable occurs weakly positively is that we can never find a contravariant subderivation for this variable when proving the subtyping relations for two recursive types, but with two exceptions. One is when the two recursive types are equal, then we do not do this check anymore. And or the recursive type being compared is a subtype of the top, as this example shows. With the help of all the definitions, we prove that all our formulation we discussed in the work, including the new specification finite unfolding rule, and the algorithmic double unfolding rule, the algorithmic nominal unfolding rule, and the auxiliary weakly positive subtyping rule, and also the original iso-recursive amber rules are all equivalent. And our new formulations are also extensible. So we have two follow-up works. One is a calculus with recursive types, record concatenation, and subtyping, which has been presented at the Aplas this year. And in this work, we support intersection types and record concatenation. The other one is recursive subtyping for all, which will appear in the POPO next year, in which we extend our nominal unfolding rule with bounded quantification. And this is all for Yaoda's talk, and thanks for listening. Hello, the mic is on.
Yep. So I believe Bruno, who is one of the authors, is online. Can you please confirm?
Yeah, we're just trying to add him on the backstage,
Sure.
but it seems like we can't do it from here. Bruno, you can type and I will repeat what you say in the chat because it seems like we can't put you on the stage. I'm not sure why, but there is no option for that.
Sure. So Bruno, can you confirm if you are here? So we would take questions and then pass them on to you. You can perhaps respond in the chat. We are able to get him on this.
Yeah.
Yeah, sure. Thanks. So we have one question over there.
Probably a crazy idea, but have you thought about iso-recursive types that are generic so that they can take like a type parameter? If that makes sense.
Oh. I'm sorry, the iso-recursive type was what?
With a type parameter, so that they take a type parameter and then they can use the type parameter on the right hand side.
The type parameter on the right-hand side. No, I think okay, the recursive type has a recursive variable on the. So I'm not actually getting what do you mean by having a.
Like you got like u of f, say and then it's equal to like the pair of int and f, right? As the list example, right? But could you take like a type parameter and say u of f of x, where x stands for type, is equal to x comma f. So now you've got a definition of a generic list type. It can take It's not just list of ints, it's list of whatever type you pass it into.
I'm sorry, I think I cannot understand the question. Can Bruno try to answer that?
Bruno, can you take the question? Or- Yes, I believe, Bruno, you should be able to unmute and speak as well. We have added you as a speaker. Is the question was the question clear to you, or shall we repeat? Would you be able to take it up?
Don't worry, we'll pick this offline, I guess.
Sure, we'll take the question offline otherwise.
Complicated.
No worries. There is some maybe internet issue at that end. I have one more question. So you talked about as I understand, this is a new formalization of the Amber types for iso-recursive subtyping rules. Does that
Yeah.
extend trivially to let's say systems that support polymorphic calls?
Polymorphic, yeah, you can check out our new work, which is going to appear on Popo 2023. So we do not extend the Amber rules, but our nominal rules at the end of the slide to support polymorphism. So in that work, we support bounded quantification, which also subsumes the polymorphism. Yeah.
All right. I guess the Popple paper is the answer to both
my
the
question
questions.
as well.
Yeah. Sure. Thank
Oh,
you.
okay.
Bruno also said that the paper is about dealing with generics. It is an extension of F less than, and it seems that I cannot speak.
Okay. No worries. So we got the answer. We'll have a look at the Popple paper as well. Thank you. Any other questions?
Thanks.
Yes, we have one. Can you please pass on the behind you?
Thank you. Thank you for the interesting talk. So the algorithmic check that you do with the double unfolding rule, does it work with mutually recursive data types or types in general?
Does it work with what? Sorry, the connection is not very good.
Mutually
here.
recursive types.
Yeah.
Did you hear?
Yeah. The recursive type with what?
The mutually recursive types.
Oh, the mutually recursive type. Okay. I don't think we can. I think the recursive type is, since the recursive type here is is a general recursive, so I don't know what's the definition of mutually recursive type.
Okay, we have an answer in the chat box from Bruno. So does that help?
Yeah, thanks.
Sure. Thank you. If there are no more questions, let's thank the speaker and let's hope you're available soon.